All right. Thank you, everyone, for coming. My name is Darshan. I'm the founder and CEO of Bigscreen. We're a social VR company building one of the more popular social VR apps where people commonly use it for watching movies with your friends. My background, I've been working in VR since the DK1 back in 2012. I started working on Bigscreen full-time in 2014. I work on everything from engineering to design, avatars, art, and the full spectrum. Bigscreen, as a company, real quick, we were founded in 2014, so we've been around for about 4 years now. We're a fully remote company focused just on VR, specifically on social VR and on how that works with screens. So content that is on flat screens. We don't make content. We don't make our own games. Instead, we bring in screen-based content that people already love. So we've been around for 4 years. We launched on all the PC VR headsets in 2016. We've been a launch title for the Oculus Go, the Oculus Touch, the Oculus Rift. We'll be a launch title for Oculus Quest as well. We're a really small team. We're about 7 engineers. We'll be probably 10 or 15 people by later this year. And we're backed by Andreessen Horowitz and a few other venture capital firms. We've raised about $14 million. We're a fully remote company. We have people in the United States, Canada, Argentina, New Zealand, a few other places I'm probably forgetting. We're a very small team, though. And today's talk is mostly focused on 2 key areas. One is cross-platform. So that's across all the different headsets from full 6 degrees of freedom headsets like the Rift and Quest down to 3DOF headsets like the Gear and Go. We'll also talk a little bit about environments, avatars, UI, and just kind of the lessons we learned as we brought Bigscreen to all these platforms with all these capabilities, and the lessons we've learned from social VR. So anybody that's thinking about building a social VR experience, or whether it's a game or just a multiplayer application like Bigscreen, or somebody that's trying to bring a Rift title to Quest, a Rift title to Go, or just trying to build for multiple headsets with many capabilities. Hopefully, there'll be some good takeaways from this talk. Just to get things started, here's what Bigscreen is used for today. So people watch videos, they bring in their Windows desktop, they can play video games, they can do anything that they can do on their Windows computer, they're now able to do in virtual environments with their friends. The most popular use case of Bigscreen, though, is watching video content, so movies with your friends in something that's kind of like a virtual movie theater. You can see here the kind of evolution of Bigscreen, though. We started on the top left. You can see a very, very early version of Bigscreen. This is in 2016, probably in March, and you can see how the avatars are very crude. The environments are very simple. We started there, and we ended up with adding more fidelity to the avatars, improving our user interface, improving the functionality and capability of our software, and increasing the fidelity and capabilities of our environments. This was a very iterative process. It took a lot of time, and it took a lot of learning from our users. We have nearly 1 million users, and that allows us to really learn from our own user base. What do they want? What features do they care about most? You'll see how our avatars were very simple, and we added some specific things like bodies and torsos, eye gazing, our environments, the seating arrangement of our environments. You can see how that's kind of a large campfire with a lot of curved logs. In this talk, we'll get to how we evolved from the very crude avatars on the top left down to the bottom right. One kind of key takeaway for me is to iterate over and over again. For us, at least, it was very valuable to put something out first, something out that was very simple, and just improve on it over time. This is really where we started. You can see how a core value of Bigscreen that we provide to our users is the content on the screen. There you can see someone's pulled up a video game on their computer screen. They can see that in VR, and they can invite their friends. Those 3 white skulls are their friends. And you get to see their screens, you get to see their head, and you get to see kind of body language as they are excited about what they're playing. You get to hear them. We have voice chat. So when they're talking to you, it's positional audio. You can hear when someone is sitting right next to you what they're saying. But this is where we started. This is very, very simple, but kind of proved the fundamental value that we wanted to provide to our users. Another key piece of Bigscreen is not just the value that we provide, but the fact that we're providing that value to our customers across all the different platforms. Over the past 2 years, as we've launched Bigscreen on the Rift and the Vive in 2016, we've brought Bigscreen to many, many more headsets since then. We're now available on almost every major VR headset, except the Daydream and PlayStation VR. Hopefully we'll bring that later this year and early next year. But designing for cross-platform is fairly challenging and something that many people will probably end up going through. And the challenges that we faced start with just the differences even in hardware capabilities. So some of these headsets, we support the Vive, the Rift, they have OLED displays, but many of them have LCD displays. And the key differences there with the hardware actually ends up affecting everything from how you design even your environments, your art, your user interfaces. The differences between OLED and LCD are situations like deep blacks. If you're watching a movie in Bigscreen, when there is a black frame on the movie, the entire environment gets pitch black. Just like in a movie theater, when you go into a movie theater and it's a black screen, the whole theater just feels pitch black. You get that experience in Bigscreen on an OLED display. But if you're on a VR headset that's an LCD display, we have to do a lot more work, a lot of tricks to try to get a darker, deeper black. That's just not possible due to the physical differences in the displays. In addition, there's issues with dithering, where the grays start to band and looks really distracting and displeasing. These are all the differences some of the differences that these headsets have, the displays have, that we have to factor in as we design for each individual headset. Similarly, there's 3DoF and 6DoF, of course. So Quest is now a 6DoF headset with 6DoF hands, but many of the headsets that we support are 3DoF headsets with just one single 3DoF hand controller, all the way up to, of course, the Rift and the Vive and PC VR headsets, which also have 6DoF heads and 6DoF hands. So when we design our user interface, when we design our environments, and all of the interactions that users have, we have to factor in how does this work for a 3DoF headset, as well as how does this work for a 6DoF headset. And that's also challenging because the easiest thing one could do is to design for the 3DoF headset, to design for a headset where you only have one controller in your hand, like the Oculus Go, and then just use that same user interface and use that same functionality across the entire spectrum, to use that even on a higher-end 6DoF headset. But that ends up crippling the functionality of the higher end. And one of the lessons we learned there was the most intuitive, natural thing that people were doing in user testing, in our user research, was that they would try to poke into user interface elements if their controller allowed them to. So when you have a touch controller, the very first thing people try to do is poke into the UI, and that was very intuitive for them, the first thing that they wanted to do. On the Oculus Go or on the Gear VR, which is a 3DoF controller in your hands, there is no way to do that, so users don't bother really trying to do that. So in those cases, we had to completely rethink how we would handle the user interface, and I'll get more into that later in the talk. The other challenges we had were even just having multiple headsets being supported inside one project, inside one repository. And these are programming challenges in terms of supporting so many different headsets and the complexities of them, and tailoring code for each headset in a manner such that you're not writing multiple projects, multiple different code snippets, copy-pasting it all over, and not making a maintainable project. Just handling multiple different headsets, multiple different runtimes and SDKs, all in one repos is another challenge. And of course, user interface also has cross-platform restrictions. So when you provide some sort of tutorial or text to your user suggesting, like, take off your VR headset, that simple phrase on the Oculus App Store might need to be phrased differently than on Steam, than on the Windows Mixed Reality Store, or on the Samsung Gear VR, because you can't say, take off your Rift for a user that might be on a Vive. And that will actually, not only is that a bad user experience, but app stores will reject your application if it doesn't reference the correct VR headset in the user interface. So that's similar to like a localization problem, but just dealing with those nitty-gritty details just makes cross-platform development that much more challenging. For us specifically, we also had to challenge ourselves to figure out what the value we would provide to our users would be on all these different headsets. So to go back to what Bigscreen is, it allows you to use your, at least on the PC, it allows you to use your PC's desktop screen inside VR. You put on your VR headset, and you can see your desktop screen, and you can do all sorts of stuff with it, whether it's gaming, watching movies, whatever you want to do on your computer, whatever you can do on your computer. Of course, on other mobile VR headsets, there is no Windows desktop for us to even bring in. So the very first challenge we had when we discussed getting onto cross-platform Android headsets was what value do we even provide to our user base? And we learned a few things there. And the broader lesson here is just trying to figure out what can you do for the user per platform, as opposed to just broadly creating something that hopefully works everywhere. We found two things. One, we realized we could stream the Windows desktop wirelessly from a computer in your home into your mobile VR headset. That gives you an untethered experience that is very similar to what you would get on a tethered PC VR experience. So we were able to find a way to bring the value that we were offering on the PC, on the highest end headsets, down to the mobile VR headsets as well. But the other key takeaway was that our users were asking us for us to come onto all these mobile VR headsets. People that used and loved Bigscreen on the highest end PC headsets kept asking for us to make Gear VR versions and Daydream versions and Oculus Go versions. And the reason for that was because their friends had these headsets. Social VR is the other important piece here for cross-platform, which is that we at least allow people on other headsets to join into the social VR experience, even if they don't have the full capabilities that a PC VR user would have. The third realization we had here was to look at what our users were actually doing, even on the PC VR headsets. And ultimately, we discovered, even though we give them the full Windows desktop in VR, even though we have the social VR functionalities and the screen sharing, ultimately the value that most people got out of our software was to watch movies with their friends. It was to watch video content with other people around the world. And we went directly to the movie studios and licensed all the content, like top movies that you would watch in a movie theater or on YouTube or iTunes today, so that we can then distribute this licensed movie content directly to people. So someone on an Oculus Go or an Oculus Quest, where the original value of Bigscreen, that Windows PC screen, where there is no screen for us to utilize on these mobile headsets, we're able to still provide the value that people wanted out of Bigscreen because we went and just got the movies that people wanted to watch and brought them right into these headsets. But this was a realization, the need to go to movie studios to license content ourselves. This is a lesson that we did not learn on day one. This is a lesson we learned a year or 2 years into development, into putting it out into the world. Because we learned this from our users. We learned what people were doing, what people really wanted out of our product, and then figured out how to bring that experience to the broader public. So to switch from cross-platform and talk a little bit about environments specifically, we had a lot of challenges as we brought Bigscreen from PC VR headsets like the Rift down to mobile VR headsets like Oculus Go. We launched on Oculus Go earlier this year, and we'll be launching on Quest next year. But one of the challenges specific to Go and to 3DOF headsets was that our environments were really designed from the beginning for a full 6DOF experience. And some of them did not work very well on 3DOF headsets. And they definitely did not work very well on Android low-power devices where we don't have the full GPU budget or the CPU budget that we have on the PCs. One of the biggest issues we hit with our environments was just teleporting around them. The earliest versions of Bigscreen, we just put out an initial attempt at how could we make teleportation happen. So teleportation, of course, being the way that you explore and move around in an environment. And our initial implementation required you to gaze at specific seats, and you would, after a short period of time, automatically move to that seat. This is fine on the Rift, and on the Go, it really starts to break, because there might be seats behind you, And to turn your entire body all the way around, you might be in a chair that is not particularly easy to turn around. It was quite a pain for users to rotate, to go and look at a seat that might be behind them. But it was even bigger of a challenge if the seat was very far away. Because if you have 10 seats in front of you and you're trying to gaze at a seat, it's very difficult just using your head alone or using a controller, a 3DOF controller alone, to try to pick exactly which seat you wanted to get to. The ultimate user interface or kind of user experience that we ultimately achieved on our Go launch was to switch to a arc-based teleporting, where you use your 3DOF controller, which you can't move it around quite a bit, but you can still arc your entire controller. And by arcing the controller, you can select kind of which depth you want to move to. We also added grid snapping that allows the user to pick exactly which seat they want to get to without worrying too much about the user being exactly correct, allowing them to move with a little bit of freedom without worrying too much about getting exactly the right seat. The other thing that we added was snap rotations. And this made it really easy for a person that's sitting in a 3DOF headset, facing a certain direction, to rotate themselves just using their controller. And that made it a lot easier and avoided a lot of the neck problems that you might have if you're constantly trying to move somewhere behind you or to just look behind you. Ultimately, though, performance has been the biggest challenge for us over the past year. Mobile headsets like the Oculus Go, this is a Snapdragon 821. It's the S7 chipset. The capabilities of these headsets are really restrictive compared to the PC where we came from. So when we were on the PC, we could easily have hundreds of draw calls in a specific environment, and there would be no issue whatsoever. We would be able to hit frame rate and still have enough budget for users to do whatever they wanted to do. However, environments on mobile VR devices, we've really had to limit them to 30 draw calls or less. Anything over that, and you really started to get into performance issues. Performance issues for us mean, at the very least, it's not a hitting frame rate. So the Oculus Go renders at 60 hertz, and the Oculus Quest renders at 72 hertz, 72 times per second. Beyond 30 draw calls on the Oculus Go, or beyond 100 draw calls as an application, you start to struggle. You won't be able to hit 60 frames per second. Environments specifically, that meant that of a 100 draw call budget, we really couldn't use more than 30 draw calls. And that limited our ability in terms of bringing a PC environment directly into the Oculus Go. One of the things that we did here was to just limit the areas in which a user could even teleport to. So we have some very large cinema environments, and you can see them here. This is a pretty large cinema that has, I think, 150 seats. On the Go, we actually just limited people to a small section of 20 seats that they can teleport around to, the 20 most popular seats. That meant that we didn't allow Go users to teleport all the way down to the front of the cinema, which meant that in those areas, we can just chop off the fidelity and really drop down to much more rough seats that don't use as many verts, that don't have as nice textures. It really allowed us to save a lot of budget in environment design by limiting the areas that people would be able to get to on mobile. Surprisingly, we've been doing this for, I guess now 6 months. Nobody has noticed and nobody has complained, which to us suggests that people didn't really care about going to those areas quite so much anyway. The other thing that we had to do is to switch over to really mobile-friendly shaders, like unlit shaders, anywhere possible, to get rid of a lot of the high-fidelity stuff that we were doing on the PC and to just limit what we were doing on mobile. And the reason why we were so ruthless in our environment design here is that battery life is critical. This is a big shift in thinking, not just for us, but for anybody that's designing for mobile VR, especially someone coming from a higher-end PC VR. And the reason for this is that every single ounce of performance that you can squeeze out of your application is an extra minute of battery life. And the average user, the average session for Bigscreen is nearly an hour long. And the Oculus Go, for example, is a device that can last for maybe an hour and a half to 2 hours. And every minute that we can get out of the device is better for watching movies that might be 2 hours long. So for us, bringing down the experience and using, when you profile your application using performance tools, you'll see that the Oculus Go has levels ranging from CPU 0 up to CPU 4 in terms of the throttling of the CPU. We wanted to do as little as possible, to use as little CPU and as little GPU as possible, just so that we could eke out just a little bit more battery life out of the device. One of the other challenges that we had bringing our environments from the PC right into mobile VR headsets was that most of our environments had rows of seats. These are very linear rows, just like where we're sitting right now today. Everybody's sitting in a row linearly right next to each other. The challenge that we hit was that people can't lean in a 3DOF headset. This is something that, of course, now is really obvious to us, but as we were going through development, we were so focused on performance and just getting it to work with a pretty tight launch timeline that we didn't realize the leaning problem, which is people that are sitting in a linear row of seats. If you have 10 friends and there's 5 people on one side and 5 people on the other side, the only way you can have a conversation, a social VR conversation where you can wave at them, you can talk with them, make eye contact, the only way you can talk to someone 4 or 5 seats down from you is to lean forward. But a 3DOF headset can't do that, which meant that every environment that we had was designed in a manner that required leaning, and it just wouldn't work. This is an issue that we found way too late, and hopefully something that you keep in mind as you're designing environments from the very beginning, so that most seats or areas where players will be are not going to be in a linear row, because you won't be able to make eye contact, you won't be able to have a conversation. So what we've been doing now is to revisit all of our environment design from scratch with this in mind. And most of our environments now, moving forward, have curved seating. So imagine a cinema that's more like an amphitheater, where every seat has a little bit of curvature to it, so that it doesn't take much for you to be able to see people that are sitting further away from you. The other meta takeaway here is to do user testing, to put this in the hands of users and to test this as much as you can in real-world scenarios. We did a lot of testing internally, but in development, that might just be one person testing the app just to see if it ran, just to see if we could hit frame rate. That's how difficult this was. But do real user testing, put it in the hands of many users, put them in a social VR scenario where you see them actually go through the full experience. You might have caught this problem a lot earlier than we did. Switching gears a bit to our avatars. We've iterated on our avatars over the years, and we'll have a completely new set of avatars coming out later this month. The avatars that we've got here, there are some pretty specific design decisions we took here. Design decisions that would affect any social VR application as you're designing it. Thinking through things like IK. IK being whether you want to have elbows, whether you want to have knees and full legs. And all of these are based on what you're trying to achieve with your own application. For Bigscreen, since we're a seated experience, we took things in a certain direction. One thing that we did was eye gaze. So none of the VR headsets we support today have eye tracking. I wish they all did, but unfortunately none of them do. And eye tracking is really important for a social VR application because it communicates so much fidelity, so much emotional language, body language. You can tell whether a person's paying attention, how they're feeling. Eye tracking is fantastic, but without any form of eye tracking, if you look at a social VR avatar, the eyes are just fixed and they're just staring forward, and it's kind of creepy. So we did a couple things here, and we did this last year, right before we launched on mobile VR headsets, is to add eye gazing, to add eyelids that blink. But we did it in a manner that's a little bit cartoonish so that we didn't fall into the uncanny valley. And the other thing that we did is develop a system that's basically points of interest to detect where would people most likely be looking at. So one of the developers on the team worked on this and is a system where you can predict the user is most likely trying to stare at an object right here, or most likely staring at a person when they're looking that way, and to snap the eyes, these fake eyes, right to what we think the person is most likely looking at. And by doing this, we can trick the users who are in this social VR experience into thinking that these are expressive eyes. Because ultimately, what matters is that it's believable and not that it's realistic. In the sense that other people in your social VR experience don't need to know exactly where your eye is. They just need to believe that that's where your eye is looking. So some of the other design decisions that we had to make with our avatars is full body IK, and whether to use it or not. Some VR experiences, games and apps have chosen to go full body IK, and some have chosen not to. For us, big screen's a seated experience. So the vast majority of the time, you're seated, you're facing forward. We don't know where your legs are because they're not tracked. The only things that are tracked are your head and your hands. We don't know where your legs are. We don't know where your elbow is. So everything else there would have to be estimated using technologies like IK. We chose to avoid that, and instead, this is a fairly common design principle these days, is to just show whatever we actually know, to render a hand model exactly where we know the hand is, and not to render things where we don't know where the object is. However, if you look at our avatars, we do have torsos, and we don't know where the torso is, but it's fairly easy to estimate where the torso is. And again, going back to believability, what matters to people in a social VR experience is not where your body physically is, where your torso physically is. What really matters is just whether it's believable that your torso is facing that way, that your torso is in that position. Because we have a head and we have a neck model, in most scenarios, the torso is right underneath it, so we can tell roughly where the torso would be, so it's believable. But for the rest, we skipped elbows. We don't have any sort of connection between the hands, so they're floating. Because otherwise, it's easy to break the sense of believability. It's easy to look like a fake game. It's easy to break that sense of presence that you would have. The other things that we have are individually customizable features, and this is really important. We wanted to allow people to look the way they wanted to look, whether it's customizing their torso or their eyes or their shirts, customizing a lot of different components. And this is, of course, important to many social VR applications, but this is really tricky to achieve on mobile and the constraints of an Android low-power CPU. The animated eyes with eye gazing we just talked about, that, of course, has some performance considerations, especially on mobile, as well as animated hands and controllers. The fidelity of an Oculus Touch and just seeing kind of the fine precision as people move their fingers, rendering that and doing that on a mobile VR headset and showing that has its own costs. Animated mouth movements is the other thing, and many avatars, like the Oculus avatars, provide like a lip sync SDK that allow you to determine what's the shape of the lip that you might want to show to a user as they're talking. Achieving all of this on mobile VR headsets coming from the Rift is quite challenging, and doing it in a manner where the avatars that you have on the PC, on a higher-end system, take advantage of capabilities of the higher-end systems without getting crippled by the limitations of a lower-power device. So this is where we started. Our PC avatars, since Bigscreen started on the PC, the avatars were around 10,000 verts, give or take, which is not too bad, but they were all 15 to 20 draw calls, which, as I mentioned earlier, we only have a 100 draw call budget on something like the Oculus Go. On something like Oculus Quest, we'll have a 300 draw call budget, but that is still really, really small. And we're talking about 15 to 20 draw calls and 10,000 verts. This is per avatar. So an application like Bigscreen supports 15 or 20 avatars in certain scenarios. One day soon in the future, we would like to have 50 avatars in a single space. This also has multiple textures, a complex shader that does multiple passes and has multiple attributes. In an environment where you have 20 users, that suddenly becomes 200,000 verts, right? Going from 10,000 verts, 15 to 20 draw calls. That's now 200,000 verts, 300 to 400 draw calls. And you can quickly see how this is impossible on a mobile VR headset. And we can't just bring in the stuff that just works on the PC. The shortcuts that we took just to get things working just don't work on other headsets. You will not render more than a frame per second, and that's a slideshow, not a VR experience. So we had to do a lot of work to achieve 20 avatars in a single space, or 30, or 40, or 50, while still hitting frame rate. And at the same time, given the fact that we're trying to create an experience that people could use for an hour on a VR headset that is untethered and powered off of a battery, every improvement that we could make to our avatars would make a huge difference. Ultimately, what we were able to achieve is a single texture atlas, a single material, a single shader, for everything, for all the avatars. We could have many avatars in a single space, and all of those avatars would be under 64,000 verts, and part of that is a Unity limitation. So we were on Unity 2017, and there is a dynamic batching functionality with Unity that allows you to take non-static meshes, like avatars that are moving, a non-static geometry, and dynamically batches them up together so that they are all under one draw call. But there's a limitation in the number of vertices in Unity 2017. In order to do that, it's actually 65K. And that limitation led us to design all of our avatar systems to batch into one draw call. But that required all of our avatars to be under that limit, which meant for if you want to have 10 or 16 avatars, in our case, we did 16. We've now been able to squeeze 16 avatars into a single texture atlas, a single material, and all 16 avatars in total would have to be under 65K verts. Here it says that we batch them down to 5 draw calls, and in some cases that might be a little bit more, but that's because avatars that are close to you, we still want to animate the mouths, we still want to do the eye gazing and other things, and that ends up incurring additional draw calls. But we're able to get something that was previously maybe 300 to 400 draw calls down to something that's much more manageable, 5. There's a lot of complexity here, because if you go back to what we're trying to achieve with our avatars, these aren't just cubes. These are each are individually customized. Some are going to have completely different meshes. Some are going to have completely different hairs, torsos, hands, completely different textures for each of them, different skin colors in the shader. Some are going to be completely different meshes, yet we need to get them all into one texture atlas. If you're making an application where you already know in advance that the only capabilities that a user would have are 16 different characters, and they're predetermined, it's no issue. You can create a texture atlas, you can create a shader where these are the only 16 options that someone has. But in our case, we might have millions of options. And what's even harder is that people might change their avatar at runtime. While they're playing the application, they might suddenly change it. So we built a dynamic system to create that texture atlas at runtime for every user whenever somebody changes their avatar. So if they change their shirt, if they change the color of their skin, that would cause everybody in the room, in the virtual room, to regenerate a new texture atlas such that all of this ultimately still gets batched down into 5 draw calls. This is the kind of effort and thinking that we had to implement on mobile just in order to hit frame rate, and is the kind of work that I would recommend thinking about as you're starting development, as opposed to us, where we're realizing this 2 years into development since we came from the PC. The user interface was the other challenging piece for us, and I alluded to this earlier. Because of the interaction differences of the platforms, we really had to think through how do we make the best possible 3DOF experience where you only have a single controller in your hand and there's no positional tracking, but also had to create something that's intuitive for a 6DOF user where at the very beginning they just want to poke something. One of the fun parts of Bigscreen is when you have that 6DOF controller, there's a lot of gestural things that we can do. To play that again, you can see that a person with a Rift controller punches their screen and the screen breaks. That's not something that a 3DOF user can do. And sometimes, this is just a fun little Easter egg that we have. That's something that we have not been able to bring to 3DOF users, and that's fine. But we didn't allow ourselves to not have something on the full 6DOF experience just because we also support 3DOF controllers. You can see here, this is, well, I guess this is actually our old user interface. We have a completely new interface coming out later this month. But in this interface, you can see how people are able to pick up objects. They're able to poke interface elements. They're able to move these elements around as well. The challenge we had was bringing this to the Oculus Go and the Gear VR, where this is just not possible. You aren't able to move out and grab. You aren't able to position stuff. You're not able to poke a button. Where we ended up landing on this is to just cater to all of this, to have 2 different interaction mechanisms. The laser pointer allows you to use a 3DOF headset, or a 3DOF controller rather, to laser into a button and to click on it. But at the same time, that same button would be able to, you could poke it. using your finger if you had a controller that supported that functionality. So that required us to design a lot of user interface components like sliders, checkbox, even dropdowns. How do each of these interface components work when you poke them? How do they work if you had a laser pointer in your hand? This is something that's an ongoing effort, and our new user interface that'll be coming out next month will hopefully improve this such that a user, regardless of platform, will be able to do something fairly intuitively. Taking a step back, as we brought Bigscreen onto Android, one of the challenges that we had, and this is a general Android problem, it's not particular to VR, is just long build times on Android. So when you're designing an application for any mobile VR headset, the challenge there is that you make a small change. You want to fix a bug or even just change some text. It might take you many minutes in order to get that new build onto your device. And this is really critical because the iteration speed that you have is ultimately how fast you can build your products and your visions and ship them. One thing that we ended up doing here is that since we already have Bigscreen running on the PC, we are able to do a lot of our work on the PC. We're able to use a Rift to do a lot of our testing, to test our user interface, to test just core functionality, like is networking even working. We're able to make all these changes on the PC, test them very quickly by just hitting play in the Unity editor, and then bringing it onto Android and creating Android builds as needed. Of course, there's a lot of work that we can only do on Android. For example, a lot of our networking code, or the vast majority of the Bigscreen code base at this point, is native code in C++ outside the Unity editor. That we can only test on device. But at least for the rest, for features that you're making, for testing avatars, try to do that on the PC. The other gotcha that we have is when you have a single Unity project, but you're supporting multiple platforms. Switching between platforms, and this is very specific to Unity, but when you're switching between platforms, meaning in the Unity editor as you're selecting build targets for the PC, it's going to rebuild the entire library. The shader cache, the textures are going to be recompressed in a format designed for that specific platform. And on a large project, this could actually take an hour or even longer. And of course, if you just want to switch and build for a new platform, it makes no sense to wait an hour each time you want to do this. That is incredibly slow. You will get barely any work done in a day. And what we found works well for us is to create two separate folders and to just copy over, to have the same code base, the same assets, everything in that, but the library folder, the project settings folder, et cetera, within Unity is just separate for each platform. This allows us to open up different instances of Unity and to have different folders of the same Unity project for each platform, such that switching platforms now is just a matter of opening up a different Unity editor and opening up that specific folder and instantly building, as opposed to waiting an hour for a platform switch. Another challenge that we had was filming footage. Once you get to the stage, the final stage, where your app is getting done and you're thinking about marketing assets and you want to create some beautiful trailers of your product, filming on the Oculus Go or the Gear VR is fairly challenging. And in our case, the experience on Oculus Go, Gear VR, Quest is quite similar to the experience on the Rift or PC VR headsets. The trick that we found works really well is to do a lot of our filming on the PC, where we have the performance headroom to film at 1080p 60 or higher, to film at 60 FPS, a beautiful version of the application. We have the performance budget on PCs to have spectator cameras, separate video cameras that are in your virtual environment that aren't necessarily what you see as a first-person perspective. So when you create a trailer, you're able to have multiple perspectives of your VR game to better communicate to a viewer what is your experience like. All of this is very hard and impossible in some cases to do on an Android device. So by filming on the PC, we're able to create much higher quality footage and do a much better job of communicating what the experience is like, as opposed to trying to connect the Android device into and just film whatever the user sees directly from that. So those are some of the kind of high-level takeaways that we found from what works for us as we went from the PC VR systems all the way down to the Oculus Go and how we built up from there to Oculus Quest and other platforms. There's a kind of wide range of topics, from environments to avatars to UI and cross-platform functionality. And happy to chat more after the talk about any more details if you're curious. Otherwise, if you have any questions, I think there are mics in both of those corners, and can take some questions now.